Video, I want to introduce two more examples that are kind of similar to the example from the first video. So let's take another one that comes from 2x2 matrices. Let's let G be GL2R, and H is going to be SL2R. So non-zero matrices, 2x2 matrices with entries in R with non-zero determinant, 2x2 matrices, entries in R with determinant 1. And K is going to be the subset of G consisting of matrices x0, 0, 1, where x is a non-zero element of R. So the determinant of such a matrix is x. So okay, definitely still in G. And it's easy to check that this is a subgroup. All right, so the idea is that these two subgroups, H and K, in some sense give rise to G, but not as a direct product. So let's take an element little g in G and let delta be its determinant. And just by being in GL2R, note that delta is not 0. We can write G as a product of something in H times something in K. This is a little bit of a trick. You just take G itself times delta 0, 0, 1 inverse. Okay, what is this matrix? It definitely has determinant 1 because the determinant of G is delta. The determinant of this matrix inverse is 1 over delta. And the product of the determinants is the determinant of the product. So this is an H. And then we'll just take delta 0, 0, 1, which is definitely in K. And it's easy to check because matrix multiplication is associative that this really is equal to G. So okay, H times K is now equal to G. And it's clear that the intersection of H and K is only the 2x2 identity matrix. Right? I mean, if you're in K, the upper right and the lower left entries are 0. So the only element of K that actually has determinant 1 is when x is equal to 1. So we can ask, is G isomorphic to the direct product H cross K? And the answer is no. There are a bunch of ways to see this, but one is to say, okay, if these two groups were isomorphic, they would have the same number of elements of order 2. And GL2R has infinitely many elements of order 2. That's a nice exercise. Remember, you can think of elements of 2x2 matrices as corresponding to linear transformations from R2 to R2. And you can describe these linear transformations in a geometric way sometimes. So you could take, for example, a line through the origin in R2 and see what happens when you reflect over that line. So you can build a 2x2 matrix out of that by saying, where does this send the first standard basis vector? Where does this send the second standard basis vector? So in this way, you can see that GL2R has infinitely many elements of order 2. I claim that the right-hand side does not. So SL2R has only one element of order 2. The negative of the identity matrix is certainly 1. And it's a little exercise to show that it's the only one. So I think maybe the easiest way to prove this is just take the matrix A, B, C, D and square it. And like see what has to be true for that matrix in SL2R to square to the identity. The subgroup K has only one element of order 2 as well, because when you square an element in K, you just get x squared 0, 0, 1. So you need x squared to be equal to 1, but x is not 1, so it has to be -1. Okay, so now the right-hand side, we know something about orders of elements in direct products. If you want an element of order 2 in H cross K, you choose an element of order 1 or 2 in H, 1 or 2 in K, and don't pick the identity in H cross K. So that gives 3 elements of order 2. Okay, so that shows these groups are not isomorphic. So what does that mean? By the recognition theorem for direct products, either H or K or both are not normal in G. And we already know that H is normal in G because it's the kernel of a homomorphism. Which homomorphism? The one that takes a matrix in GL2R to its determinant. So it goes from GL2R to R star, and SL2R is exactly the kernel. So what does that mean? K is not normal in G because if it were, then the recognition theorem for direct products would say that G is isomorphic to H cross K, and we've just seen that it isn't. Okay, so G is not isomorphic to a direct product of H and K, but there's still some nice sense in which G is built out of H and K. And that's what we're building towards in this lecture. So I'll pause and erase, and I'll do one more different type of example that doesn't come from 2x2 matrices. Let's look at an example that doesn't come from matrices. Let's take G equals Sn, where n is at least 3, and H to be An. So we know this is an index 2 subgroup of G, so it's normal in G. And let's take K to be the cyclic subgroup generated by the single transposition 1, 2. So we know that K is not a normal subgroup in G. For one thing, this was on the first midterm, but you can just conjugate by an element like the transposition 2, 3 and see that that does not fix this subgroup K. It's clear that the intersection of these two subgroups is the identity matrix because H is all the even permutations. The only non-identity matrix in K is odd. Also, H times K is all of G, is all of Sn, because every odd permutation in Sn can be written as some even permutation times the single transposition 1, 2. This was an idea that we saw when we were computing the size of An for the first time. So the number of even permutations and the number of odd permutations is the same because there's this bijection where you send an even permutation to the product of that permutation times 1, 2. And that gives a bijection between even permutations and odd permutations. All right, well, is G isomorphic to the direct product H cross K? We definitely can't apply the recognition theorem for direct products because K is not normal in G. And we can check that, in fact, G is not isomorphic to this direct product. The left-hand side has trivial center. It's a nice exercise to show that the center of Sn is trivial for all n at least 3. Given any permutation, just write down some permutation that doesn't commute with it. The right-hand side, though, has non-trivial center. I mean, in particular, there's a subgroup of H cross K consisting of the identity in H and K. So that's a non-trivial element of the center or subgroup in the center. So these groups are not isomorphic. Okay, so in these first 3 examples we've seen, we have 2 subgroups H and K. We see that the product set HK is the entire group G. H intersect K is the trivial subgroup. And in each of these 3 examples, H was a normal subgroup in G and K was not. And in every one of those examples, G was not isomorphic to the direct product H cross K. So let me just quickly do one more example, which is a little bit different, and I hope that you see how. So let's say G to be S4, and let H be a CeLO 2 subgroup of G, so it has order 8, and K to be a CeLO 3 subgroup of G, so it has order, biggest power of 3 dividing 24 is 3. Okay, so we can check, this is something we've done before, that the number of CeLO 3 subgroups is 4, and the number of CeLO 2 subgroups, I can't write and think at the same time, the number of CeLO 2 subgroups is 3. So neither one of H and K is normal in G because a CeLO P subgroup is normal in a group G if and only if there's a unique CeLO P subgroup in G. It's clear that H intersect K is the trivial subgroup by Lagrange's theorem. If a subgroup of size 8 and a subgroup of size 3, they certainly intersect only in the trivial subgroup. Okay, so now what can we say about the product set HK? Well, how big is it? You know, the size of HK is the product of the size of H times the size of K over the size of the intersection. So if the size of the intersection is 1, the size of this product set is 8 times 3 is 24, which is the size of all of S4. So that means that S4 is equal to HK. Okay, so is S4 isomorphic to H cross K? No. We know that a finite group G is isomorphic to a direct product of its CeLO P subgroups for overall of the P dividing the order of the group, if and only if there's a unique CeLO P subgroup for each P dividing the order of the group. So S4 is not isomorphic to this direct product. What is different about this example than all the others? In all the other examples, we had these two subgroups H and K, and H was normal in G and K was not. And in this last example, neither one of the two subgroups is normal. Okay, so these will be some examples that we'll come back to later in this lecture and also the next one when we talk about semidirect products.